All right, now we need to talk about what has often been called the most important equation in all of astrophysics, certainly a very powerful and important idea. We're going to talk about Newton's version of Kepler's third law. Newton's version of Kepler's third law. All right, you remember what Kepler's third law is. Kepler's third law, plain vanilla Kepler's third law, applies to all objects which orbit the sun. The planets, and now we know it applies to all asteroids and comets and everything that orbits the sun. Kepler's third law says that p squared is equal to a cubed, where p is the period of time of something to orbit the sun in years. A is the semi-major axis of the object's orbit, measured in AU, and if you square the period and you cube the semi-major axis, these numbers are equal to each other. Okay, what Newton does is he, through the course of his law of gravity, explains why they do that. Well, it's the masses, it's the force of gravity between these masses which is causing this to happen, and so he is able to derive this from more basic principles, and he shows us that m1 plus m2 equals 4 pi squared a cubed over gp squared. Now, don't be scared. We're going to get at the most important aspects of this equation, and it's not ridiculously evil. All right, first of all, he says the sum of the masses, so these two masses of these things, so if the Earth is orbiting around the sun, that's the mass of the sun plus the mass of the Earth, is equal to 4 pi squared. Okay, numbers. There's capital G. That's a constant. A universal constant, which we're not going to use in this class. And then we've got A, which is the semi-major axis of the orbit, the distance, in this case, the distance between the Earth and the sun, and P, the period of time it takes for the Earth to orbit around the sun. Now, notice this. In Kepler's original third law, the plain vanilla ordinary third law, it's a relationship between two quantities, distance from the sun and period of time, that it takes to orbit the sun. In this case, this applies to everything. This applies to anything in the entire universe. Anything where you have got one object orbiting another object, then Newton's version of Kepler's third law applies. So the first thing, it applies to not only planets orbiting the sun or other things orbiting the sun, it applies to the moon orbiting the Earth, it applies to Jupiter's moons orbiting Jupiter, it applies to stars or our sun orbiting the center of our galaxy, galaxies orbiting around each other, masses orbiting around a black hole. Everything in the entire universe can be understood with Newton's version of Kepler's third law. And so over here, so he says, okay, now it's a relationship between three quantities. Orbital size, orbital period, and now we've got mass involved. So what does this mean? It means if I take A, the distance from the Earth to the sun, 93 million miles or whatever, 1 AU, and P, the period of time, 1 year for the Earth to orbit the sun, and I do a whole bunch of math, this can tell me what the total mass of the Earth and the sun is. And the total mass of the Earth and the sun is basically the sun. And this is often what we see. Usually when we're studying objects, we're studying one big object orbiting by one little small object. So what we're going to do in this class is we're going to say, it's the sum of the mass of the sun plus the mass of the Earth is basically the mass of the sun. So let's totally ignore the mass of the Earth. So in this class, as long as the masses are very unequal, which they often are in astrophysical contexts, then this gives us the mass of the thing being orbited. So we're mostly going to ignore the second object, assuming it's very small. And so what this means is, using this equation, I can use the orbit of the Earth around the sun, I can use the details of the orbit of the Earth around the sun to tell me what the mass of the sun is. You want to know what the mass of the sun is? You take any object that orbits the sun. Earth, Mercury, Venus, any of the planets, it doesn't matter. If you take, okay, Mercury is this distance from the sun, it takes this many months to go around the sun, you put those numbers in there, you can calculate the mass of the sun. Or you could have used Pluto. Pluto's distance from the sun, it takes 200 whatever years to go around the sun. It will give you the same mass of the sun. They're all orbiting the same thing, so you get the same number out of it. If you want to know the mass of the Earth, well, what do? Well, you need something that orbits the Earth, like, say, the moon. The orbit of the moon around the Earth tells you everything about the mass of the Earth, nothing about the mass of the moon. The orbit of the Earth around the sun tells you everything about the mass of the sun, nothing about the mass of the Earth. Let's write this down. So this is what we're going to do. Newton's version of Kepler's third law is going to be our scale. We will use it to measure mass. if I want to know the mass of any object in the whole entire universe, according to Newton's version of Kepler's third law, all I got to do is find something else that orbits around it, measure the orbital distance, how far away is it, measure the orbital period, how long does it take to orbit, and that allows me to calculate the mass of the thing being orbited based on the motion of the thing doing the orbiting. So, orbiting. We'll use it to measure mass. So, orbit of Earth around the Sun tells us the mass of the Sun. The orbit of the Moon around the Earth tells us the mass of the Earth. The orbit of Moon around the Earth tells us the mass of the Earth. And this is interesting. So that means the orbit of the Earth around the Sun has everything to do with the mass of the Sun, nothing to do with the mass of the Earth. If you took half the Earth, if you took the Earth, chopped the Earth in half, threw half of the Earth away, that other half of the Earth, as long as it kept its same velocity, would continue orbiting the Sun in exactly, precisely the same way as it always did. If you took half of the Moon, if you took 90% of the Moon, you chop up the Moon into little bits, you throw away most of them, you leave one tiny little bit, and it could orbit exactly around the Earth in exactly the same, whatever, 27, 28 days, the way it always has, at the same distance, and nothing would change. The mass of the Earth has nothing to do with its orbit around the Sun. The mass of the Moon has nothing to do with its orbit around the Earth. It's all about the Earth. You use Jupiter's moons to tell you the mass of Jupiter. You use the orbit of the Sun. The Sun orbits around the center of our galaxy once every 200 and whatever million years. It's 30,000 light years to the center of our galaxy. Our Sun orbits around our galaxy every 200 and something million years. It's 30,000 light years from it. Using that, I can calculate the mass of our galaxy. I can calculate the mass of anything in the universe based on the characteristics of some object orbiting around it. And so if object A orbits around object B, then object A is telling me what B's mass is. And we know nothing about object A's mass, and that's a really important thing. Okay, we got to do a couple quick examples in order to see how we can do this mathematically. Let me again, write it down. Mass equals 4 pi squared A cubed over GP squared. I want you to ignore the 4 pi squared and the g. Those are constants. We're not going to deal with those in detail here. But the a and the p, that's the engine of this equation. This says mass has to do with orbital size cubed and has to do with orbital period squared. So, here's an example. Suppose I have two planets, planets A and planet B. And both of them are orbited by moons. And planet A has a moon, moon P, which, not P, that's a bad letter for it. It has moon C, which orbits at this distance, and moon B has a moon called D, which orbits at this distance. Okay, so we got two moons, and suppose they both orbit in the same period of time. It takes 2 weeks for moon C to orbit planet A, and it takes 2 weeks for moon D to orbit planet B. So the periods are the same. So the periods are the same. So in this equation, well, P isn't, that's going to be irrelevant there. The key thing is A, the orbital distance. How far are these moons from the planets they're orbiting? And since this is half as much as this, since moon D is twice as far from orbit B, so these guys are orbiting around, and they orbit in the same period of time, but notice this one has to go twice as far. This is a much bigger orbit. That means there must be stronger gravity here. Planet B must have more mass in order to hold D in its orbit, and so that it can go around twice as fast as this moon, and it's twice as fast and it's farther away, so there must be a lot more mass here. Planet B must have a lot more mass than planet A. And here, this equation says that mass depends on orbital size cubed. Let's take the ratio of that. This distance divided by that distance is 2. The distance to moon D is twice as much as the distance to moon C. So the ratio, so A for moon D and A for moon C, well, that is 2. And so if I cube that, cubed, then I get 2, and I cube it. Cube it. That means 2 times 2 times 2. 2 cubed is 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8. What this means is that planet B has 8 times more mass than planet A. Cool. Check that out. Planet B has 8 times more mass than planet A because the moons orbit in the same period of time, but this has a distance twice as much as that. And since mass is proportional to orbital size cubed, you take the ratio, you divide these two distances divide by each other, you get 2, and then you take that ratio and you cube it. 2 cubed is 8. Planet B has 8 times more mass than planet A does. Now let's do the other example. Suppose I've got 2 planets. Let's call these planet X and planet Y. And suppose they have moons that orbit around them at exactly the same distance. If I could draw, I'd make these circles the same. So let's call this moon U, and this is moon V. And suppose the distance to U is equal to the distance to moon V. Or sorry, those should be A's. There we go. The orbital semi-major axis, the distance to moon U, is equal to the semi-major axis to moon V. So, but they orbit in different periods of time. Suppose this one takes, I don't know, suppose this one takes 1 week to make an orbit, and this one takes 4 weeks to make an orbit. So this one goes around 4 times in the time it takes this one to orbit once. So what does that mean? Well, which planet has more mass? Planet X has more mass. It has to have hugely more mass in order to hold on to this planet, which is this moon, which is orbiting 4 times faster than that one. How many times more mass? Well, I take the ratio of the periods. So I take the period of V and divided by the period of U. Well, that's 4 weeks divided by 1 week. Oh, it's 4 times as much. This has an orbital period 4 times as much. And this says mass is inversely proportional to orbital period squared. 4 squared equals 4 times 4. 4 times 4 is 16. And so that means that this one, whose orbital period is less, must have 16 times more mass. The mass of X must equal 16 times the mass of Y. Must have a lot more mass because this thing's orbiting or screaming around at huge speed, whereas this one orbits at a speed only 1/4 as much. And this is how we do Newton's version of Kepler's third law. This is how we're going to do it. And I think that gets to the really engine of it, so we can really understand what's going on inside Newton's version of Kepler's third law. Notice that this tells me nothing about the masses of the moon. Moon U and moon V can have, I don't know, this one could be tiny, one could be big, this one could be bigger, that could be smaller. The orbits tell us nothing about the things doing the orbiting, and it tells us everything about the things being orbited. It tells us the mass of the planets, not the masses of the moons. The orbits, these things cannot tell us the slightest thing about the masses of the moons. And so if I want to know the ratio of the masses of the planets, I say, well, what's different here? Are they different in orbital size? If so, take the ratio and cube it. Are they different in orbital period? If so, take the ratio and square it, because mass depends on orbital period squared and depends on orbital size cubed. And using that idea of Newton's version of Kepler's third law, we can measure the mass of everything. We can measure the mass of every planet, every star, every galaxy, every black hole, anything out there that has some, as long as it's got something orbiting around it, we can figure out what its mass is. And that is an amazingly, gloriously, wonderful, powerful tool as we go out to explore and study the details of the universe.